We are live. What's up, guys? This is Dem Keys, and today we're going to be doing a bit of a short stream because I started the stream late. That's completely on me, but I kind of wanted to keep the the streak going. I didn't want to, miss one of the streaming days. I want to make this go as long as possible. Obviously, at some point in the future, I'm going to end up having to not stream, not do a talking stream. But I'm hoping I can, stretch this as long as possible. But whenever I do need to, take like a day off, I'll eventually take it. But yeah, anyways, today, even though it's going to be a short stream, I wanted to do a bit of a yap sesh just to discuss where we go from here. So, okay, we've learned how to, or well, we are close to finishing learning. We've pretty much almost learned. Like, I mean, I still have to like officially complete that training section where we optimize the model parameters. So far, we've gotten to the part where we calculate the loss, but then what what do we actually do with that loss value, which is generating the gradients, and then based on the gradients updating the weights and biases. All of that stuff we haven't done yet. To be honest, even the loss calculation thing, we haven't done that. We haven't done that practically yet. But we are pretty close to finishing that whole training section. So I kind of wanted to go over, or well, brainstorm. Not sure what's the right term to use there, but I kind of wanted to go over where we should go from here, because I remember mentioning that I wanted to learn about convolutional neural networks and recurrent neural networks, and after that jump to transformer neural networks. I'm not sure how to say that. Transformer based networks. So, okay, let's create a thing here. Where do we go from here? This is in terms of research. So we want CNNs, and then RNNs, and then transformer, which the interesting thing is when you look into, and like even when we've looked into the transformer architecture in the past, it's been mentioned that the transformer architecture is able to perform certain things. I mean, it's able to perform a bunch of different things, but there are certain things that it's able to perform better than recurrent neural networks. So RNNs used to be used for certain things, like I believe they were also used for input sequences, like when you have a sequence of inputs that all have some sort of semantic meaning within or to each other, not within each other, that have some sort of semantic meaning to each other, like a sentence, for example. But now you're able to do it with the transformer architecture, because the transformer architecture is apparently able to perform whatever the RNN was doing, but in a much better way. I don't know if it's better performance wise, or if it's better accuracy wise. Might be both. I'm not sure. Either way, I do wanna learn about RNNs just for the sake of completeness. And I mean, there's a bunch of others as well that I have seen mentioned, which at different times we are probably gonna look into each of them as well. Like there's something called LSTM. I believe it stands for long short-term memory. And then there's something called GRU, which is I forgot what GRU is, but there's a couple of different uh, components and a couple of different architectures as well that we need to that I want to explore, but maybe not go too deep into them, because these are the three architectures that I want to go deep into right now. Um, and one of the reasons for that is because apparently a bunch of other more complex architectures that we're going to jump into later on, they all use components from these architectures in some way. Hold on. Let me open up. Uh, is there access to NN? Okay, NN module. From here, let's take a look at the namespace itself. Right. So here we have the list of all the various functions that the NN module provides, and some of these, like okay, some of these are grouped as convolutional layers and linear layers and transformer layers and recurrent layers. So that makes it a little bit easier for us to pick specific functions to focus on. But I feel like exploring this entire section is going to be beneficial, because I mean after we finish exploring convolutional neural networks and, well, RNNs and transformer networks, there's going to be, like, we're going to have to decide where to go from there as well. And I kind of want to go into more complex architectures from there. I do also want to explore STT and TTS. I was planning on doing that in the past. Okay, so let's take a look at recurrent layers. Okay, so GRU and LSTM are part of recurrent layers. So apply multi-layer long short-term memory, RNN, to an input sequence. Okay, and transformer also has its own thing, which is down here. It's pretty short, but um, I believe both encoder and decoder have more complex stuff going on within them, and apparently you can also build your own transformer layers. So I'm guessing the architecture is open to customization, which I guess we can explore that as well. I think we should explore that as well. Accelerating PyTorch transformers by replacing transformer with nested tensors and torch compile. Okay, hold on. I just remembered something. Where does attention come in here? So we have multi-head attention, which is part of nonlinear activation functions. Okay. So this, I believe, gets used in, yeah, this gets used in transformer architecture. You know what? Yeah, we should probably read this paper. Attention is all you need, because this describes the transformer architecture, and it's probably going to go into uh, detail with um, how the architecture is supposed to be built. Let's take a look at the HTML version of it. I like that in archive some of the papers, they are viewable in an HTML format. Okay, so let's take a look at. Okay, so this right off the bat, this mentions recurrent neural networks. It says recurrent neural networks, long short-term memory, and gated recurrent neural networks in particular have been firmly established as state-of-the-art approaches in sequence modeling and transduction problems such as language modeling and machine translation. Numerous efforts have since continued to push the boundaries of recurrent language models and encoder-decoder architectures. Hold on, encoder-decoder. That's another one I should look into because I know that that's specific to the transformer architecture, or at least it's heavily used in the transformer architecture. But I need to see if it's available elsewhere as well. Apparently not. Okay. Now, where was this? Okay. Recurrent models typically follow computation along the symbol positions of the input and output sequences. Aligning the positions to steps in computation time, they wait, what? Aligning the positions to steps in computation time, they generate a hidden sequence. Hold on, dude. I'm not reading this wait. Okay. Aligning the positions to steps in computation time, they generate a sequence of hidden states um, as a function of the previous hidden state and the input for position t. This inherent this inherently sequential nature precludes parallelization within training examples, which becomes critical at longer sequence lengths as memory constraints limit batching across samples. Okay, recent work has achieved similar improvements in computational efficiency through factorization tricks and conditional computation, while also improving model performance in case of the latter. The fundamental constraint of sequential computation, however, remains. The fundamental constraint of sequential computation, however, remains. Attention mechanisms have become an integral part uh, of compelling sequence modeling and transduction models in various tasks, allowing modeling to allowing modeling of dependencies without regard to their distance in the input or output sequences. In all but a few cases, however, such attention mechanisms are used in conjunction with a recurrent network. In this work, we propose the transformer, a model architecture eschewing recurrence and instead relying entirely on an attention mechanism to draw global dependencies between input and output. The transformer allows for significantly more parallelization and can reach a new state of the art in translation quality after being trained for as little as 12 hours on 8 P100 GPUs. Okay, all right. So out of this, some of it I can understand, some of it I cannot, like input embedding and multi-head attention. I haven't gone into these topics yet, but then there's this kind of stuff, um, like add and norm, and I'm assuming add and norm is just adding and normalizing. I'm not sure. I'm gonna have to look into that. And then of course feed forward neural network, and then there's stuff like linear and softmax. Those we already know, but Okay, now we are slowly starting to get to the point where we are able to understand more complex architectures. So I need to look into multi-head attention. Allows the model to jointly attend to information from different representation subspaces. What else was I going to look into? Diffusion. Because I remember when stable diffusion had come out, diffusion models were like a big thing at the time. There was a big craze surrounding them. So I'm wondering if there's like I believe there was. Okay, so diffusion by itself, I don't remember if it does use. Hold on. Let's try asking this question to a language model. Give me a second while I open up labs.perplexity.ai and okay. So instead of asking DeepSeek, we're going to ask Sonar because I want a quick answer right now. But later on, I'm going to ask DeepSeek as well by myself, just so I can get like some extra information because DeepSeek is going to show its whole thought process. And in that thought process, there's going to be a bunch of very interesting information. Okay. Um, I'm currently learning about the transformer architecture. I'm curious if diffusion models use the same architecture or if they use their own architecture. I guess I'm trying to, well, okay. All right, give it a second. Um, okay. So, diffusion models and transformer architectures are fundamentally different in their traditional designs, but there are cases of integration where transformers are used within diffusion models. Diffusion models, standard architecture. Diffusion models are generative models that gradually add noise to data uh, in the forward process. Okay. And learn to reverse this process to recover the original data distribution, which is the reverse process. Hold on, that's interesting, dude. Wait a minute. I should also look into if wait, give me a second. I should look into if PyTorch has diffusion. Denoising diffusion, okay. Diffusion model from scratch, accelerating generative AI, diffusion fast, okay. Oh wait, it did mention that this uses its own architecture. Hold on. The most common architecture used in diffusion models is UNet, a convolutional. Okay, so I believe UNet is available through PyTorch. Is UNet a convolutional neural network specifically optimized for tasks like denoising and image synthesis? UNet is well suited to diffusion tasks because its skip connections allow the model to integrate both global and localized information efficiently. Transformers in diffusion models. In some cases, transformers have been incorporated into diffusion models to replace UNet. These are called diffusion transformers, or DITs. Okay. Diffusion transformers leverage the attention mechanism of transformers to capture dependencies over long ranges and handle tokenized representations effectively. This replacement was this replacement was motivated by the transformer's success in other domains like NLP and vision tasks. Unique features of diffusion transformers. Okay, all right. Now, there was a thing. Where was it? Here. So I don't think it was in this specifically, but it there is. I think it's in torch.models. Yeah, it might be. It might be in that. Hold on. Let me, because there are certain model architectures that are available with PyTorch out of the box. Okay, hold on. Just a second. All right, so I can't find the specific thing that like within PyTorch where it says that, you know, we can there was a thing, definitely. Like we could download a thing. I just can't seem to find where it was. Like I don't think it has to come from Tim. Why am I not able to find this? Give me a second. PyTorch UNet namespace. Okay, let's try PyTorch ResNet. Okay, so there's ResNet under Torch Vision. So maybe it's because it's under Torch Vision that I wasn't able to find it. Right, so this is ResNet. What is this under? This is under models and pre-trained weights. Okay, so this is not directly under the Torch namespace, which is probably why we couldn't find it. But here is the list. Yeah, there it is. Now, UNet is not mentioned here. Maybe I need to look into that later. But there's a bunch of others that are mentioned, and of course, there's always Tim, which we can use to download whatever architecture we want. We have like a whole list of vision-related functions and like entire models available. Which, you know what, we should do that at some point. Like we should experiment with building more complex networks out of these multiple different components that are meant for, you know, various different architectures, like basically mixing and matching. Which, I mean, to be fair, that's kind of how a bunch of the more complex architectures are built. They kind of mix and match the various components that we see built for different types of architectures. They mix them up to build a more complex architecture. I'm saying that they mix them up, but like it's a lot more complicated than that. They do a fair bit of research before just randomly plugging things into other things. Okay. Quantization, dude, I should look into quantization as well. Yes, I should add that to the list. Give me a second. Quantization. Oh, also torch compile. Um, and what should I do here? For fast code and Onyx. Okay, back to this. So, unique features of diffusion transformers. Tokenization. Inputs, example, noisy image embeddings, are broken into tokens which are processed by the transformer layers. Positional and conditional embeddings. Transformers in diffusion transformers use positional embeddings and incorporate conditional information, example text or label embeddings, to guide the denoising process. Okay, versatility. Diffusion transformers can exhibit superior scalability and efficiency in handling certain generative tasks, showing competitive or better results in metrics like um, something inception distance compared to U-Net diffusion models. Comparison of diffusion models and transformers. While diffusion models typically use U-Net or a similar architecture, transformers are a separate class of models designed for tasks involving sequence and attention mechanisms. However, the advent of models like diffusion transformers indicates a merging of these paradigms where transformers act as the computational backbone of diffusion processes. Conclusion. While diffusion models traditionally do not use transformer architecture, the emergence of diffusion transformers demonstrates a successful integration of transformers into the diffusion modeling framework. This is evidence of the flexibility of diffusion models, able to support various architectures as long as they can hold on able to support various architectures as long as they can model no, as long as they can model noise effectively. My God, dude, why? What is going on? Holy shit. Okay. Anyways, give me a second. Yeah. Okay. Right. So from here, after we are done with this, after we are done with learning the training process, actually, you know what? I wonder if I should maybe put Torch Compile up here because I did want to explore, um, well, I wanted to explore Onyx specifically, but because we are going to be using Torch Compile for that, so I kind of also want to explore the Torch Compile side because Torch Compile can be used to compile compile faster code. Like it converts your whatever your model code is, your model architecture code. It basically converts that into a more faster version of it, and you don't need to like save that anywhere. Usually, it just gets like PyTorch handles the whole um, saving process. It's not really saving. You're caching it. So the first time that you compile the code, it gets saved somewhere. It gets cached somewhere, and then the next time that you need it, or the next time PyTorch needs it, it's just going to use the cached version. So yeah, okay, maybe I should explore Torch Compile next, and more specifically focus on fast code and Onyx. Okay, now um, so I'd mentioned earlier that this is going to be a bit of a short stream, and that's completely on me because I started the stream late. Hopefully tomorrow I'm going to start it earlier, and then we can go for, maybe an hour and a half or 2 hours, or let's see how long I'm able to go. I want to gradually start going for longer as well. I mean, I don't want to like stretch it for too long, but like I want to try going for a little longer than, because like I've gotten comfortable with doing 1 hour, 1.5 hour. I want to try and stretch it a little more, um, and see how that goes in terms of both my voice, but also um, being able to continue doing whatever research I was doing. But anyways, okay, that's gonna be it for today's stream. We are gonna raid into Little Witch Oz. Oz is a friend. Oz is cool people. We raided Oz yesterday as well. Today she is playing Path of Exile 2. But yeah, that's gonna be it for today's stream. I'm gonna try and stream again tomorrow. Hopefully, I'm able to do a talking stream tomorrow as well. Uh, but yeah, dude. Uh, I hope you guys have a nice day, and I'll see you all next time. Peace.